And as you might know, Glueballs are very close to my heart. But what is even closer to my heart are people, and therefore, I would like to do the following. So, because we have a birthday child here, very.
Once a year we celebrate with stupid hats and plastic plates. The fact that you were able to make another trip around the sun. And the whole clan gathers round and gifts and laughter do abound. We let out a joyful sound and sing that stupid song. Happy birthday, now you're 1 year older. Happy birthday, your life still isn't over. Happy birthday, you did not accomplish much, but you didn't die this year, I guess that's good enough.
Let's drink to your fading health and hope you don't remind yourself your chance of finding fame and wealth decrease with every year. Does it feel like you're doing laps and eating food and taking naps and hoping that someday perhaps your life will hold some cheer? Happy birthday! What have you done that matters? Happy birthday! You're starting to get fatter. Happy birthday! It's downhill from now on. Try not to remind yourself your best years are all gone. If cryogenics were all free, then you could live like Walt Disney and live for all eternity inside a block of ice. But instead your time is set, this is the only life you get. And though it hasn't ended yet, sometimes you wish it might. Happy birthday! You wish you had more money. Happy birthday! Your life's so sad it's funny. Happy birthday! How much more can you take? But your friends are hungry, so just cut the stupid cake. Happy birthday! Happy birthday! Happy birthday!
Oh.
Stanley, Dickie, Bob,
starts with a weather.
Okay, happy birthday, George. Okay, but now I come to the other topic, which is really close to my heart, and Glueballs, they are so fundamental. If you read the first paper, which was done by Fritsch and Gell-Mann about current algebra, quarks and what else, you can read there that already the question of glue plays a central role, because they say, can we obtain these quark-free operators by investigating discontinuities and coincidence of coordinates characterizing quark and anti-quark fields in the model? At any rate, we certainly want these quark-free operators included in the extended algebra. So, but when we talk about Glueballs, and when I give you this review, I first must make a disclaimer. Since this is a review, I want not only to review the experimental facts, but I want to give you as well a glimpse on the theories about this. And of course, I don't understand the theories behind it in very much detail, but I want to give you somehow the facts and the results that the theories are based on and the spirit that they are on. So when we talk about Glueballs, the first models of Glueballs were something like that you had some constituent gluons, similar like in a quark model, and they were bound, and you make up some level of states. So that, and you had a bag model for Glueballs. So that is one picture, how you can view a Glueball. Then, more modern picture, or a different picture, that you calculate Glueballs on the computer by lattice gauge theories. This is not a picture of a Glueball. This is a famous picture of a quark-antiquark bound by a flux of glue here in the middle. And but in a similar way, you can describe a Glueball on the lattice as a closed loop on the lattice. And there are famous results that you can find in PDG. So Glueballs spectra have been calculated according to the quantum numbers, and I think everyone more or less agrees that the lightest Glueball is a 0++ Glueball, lying around 1.6 GeV. And then you have the Glueballs with all other quantum numbers. But this is actually a calculation which is now 20 years old, and there has not very much been done in this field on Glueballs. Another perspective that people look at is in recent years is to do a connection to string theory. And this was possible since Maldacena in 1997, the appearance of ADS, so anti-de Sitter space, and CFT conformal field theory, which basically connects a quantum field theory at strong coupling to the gravity theory at weak coupling. And so the slides that I'm going to give you, the spirit on this, they were mostly taken from a group in Tel Aviv by Kobe Sonnenschein and so on. And here you find some references where the slides that I stole from him are based on. And you can read there everything which is available. So, string theory. Well, you know, string theory, you have a 10-dimensional space, and when I see papers from colleagues or even theses from colleagues like Haman Nikolai about string theory, I even don't understand the title because it's so complicated to me. But what I understand is that you have to reduce this dimension to our 4-dimensional world because we are living in a 4-dimensional world. And that you can do by these gauge gravity correspondence. And so in order to do so, you need to break some supersymmetries, and there are ways which were introduced as far as I understand by Wilson. And so this basically means you come from the 4-dimensional physics is included in the higher dimensional geometry. And then you have the conformal anti-de Sitter space, which makes it curved. And then you introduce a confining wall, which is an extra scale. It comes here. And you then do some connection to the Hawking radiation of a black hole. So you get then a small curvature and a strong gauge coupling, which we have in QCD. And Wiedner has then made a model of the confining background. And basically, you get one dimension which is interesting, which is the energy scale. And so what you of course have to do is you go to a large number of colors. You go to the large NC limit, and you introduce not only D8 branes, but anti-D8 branes in order to assure that chiral symmetry is kept. So this was done in the Sakai-Sugimoto model, which was kind of the leading to the transition to QCD. And basically, you get then a space and a curved Siga geometry. So we are introducing these branes here at a certain energy level, and then you do the suppression of supersymmetry breaking and all this, and you get to our 3+1D world. And so basically, you then get to mesons by connecting the string to a so-called flavor brane. So the flavor brane are our quarks that we have in our real world, the up-down quarks, the strange quarks, the charm quarks, and so on. And they live on a flavor brane, which has a certain energy level, and then the string connects the two quarks. So the structure of a holographic meson is connected to a large mass flavor plane. You remember, this energy, this scale was the energy scale, so connected to the masses of the quarks. And so the quarks live on a certain mass brane, and then you have the string connecting, going down to the wall, to the infrared wall, and then coming up, and there's the other quark. So this is basically, if you remember the picture from the lattice, you have a quark, antiquark, and a gluonic string in between, and here you have the string, just that it falls down to the infrared wall and connects the quark and the antiquark. And you get, for example, a B meson living on the B meson brane, and here are the C mesons, the charm mesons, here are the strange, and here are the up and down, and so a B meson would look like one quark sitting on the B meson brane and one sitting on the light quark brane. So now the question is, I was talking about mesons, but how do Glueballs look like? Well, what are Glueballs in this picture? And Glueballs, since they do not incorporate quarks, it is natural to assume that they are rotating closed strings. And the angular momentum is associated with the rotation of the folded closed string. So we are sitting close to the wall, and then you have a closed string that rotates, which then is the angular momentum. Okay, so, and within this model, you can make predictions, and I will compare these predictions with the experimental results. But experimentally, we have to find Glueballs. How do we do that? Well, we have to produce them. They don't exist naturally in our world. And if you look at particle production, if you want to get to Glueballs, we better do gluon-rich processes. And gluon-rich processes are, for example, the central production in very high energetic proton-proton collisions, which is believed to be done by a double Pomeron exchange, so a high glue environment. So there were experiments in the past at CERN, WA79, WA102. You can get rid of the quarks that you have initially, because you would like, with the Glueball, no quarks present, by the annihilation of, for example, a charmonium state, a charm-anti-charm state, where a photon takes away, let's say if you have a J psi, takes away the quantum numbers 1 minus minus, and then you are left with glue, and the conventional picture is that they decay via 2 or 3 gluons, dependent on the quantum numbers this charmonium state has. And there were old experiments, Mark III and DM2, and the more modern ones is that we are running is the best experiments in all its incarnations. The third way to get a gluon-rich environment is proton-antiproton annihilation, which is supposed to be gluon-rich. And there were experiments at CERN, Asterix, and Crystal Barrel. And since I was in Crystal Barrel, I will show you some results on that. Then there was the Obelix experiment. And then at Fermilab, there was a A835. E8760 was a predecessor, and then it was followed by E835. And in the future, we are talking about PANDA, and it's clear the annihilation of a quark and an antiquark leads to gluons, and so you get a gluon-rich environment where you have a good chance to form a glue ball. And glue balls are much less likely to be formed in other hadron beams. So in a Pion beam or in a kaon beam, there were other experiments looking for glue balls. But an interesting facet in identifying glue balls are two photon collisions, because a photon in first order doesn't couple to a gluon. So if you have two photon collisions and you produce particles there, then you are pretty sure that it's not a glue ball. So two photon collisions, they act actually as an anti-glue ball filter. And so that is what Barbar, Bell, and nowadays we are studying at BESS3. So where do we stand with our searches for glue balls? And let me start with the lowest lying glue ball. Let's look at the scalar particles, so the JPC 0++. And for the scalar mesons, there's quite a number of mesons there. Known scalar mesons, the A0, F0980, the F0500 or the sigma, the kappa 700, the A0 1450, F01370, F01710, and K0 star 1430. So these have been found, and then we started in the early 90s an experiment with the crystal barrel experiment at CERN, at Lear, in proton-antiproton. And it was a 4-pi detector for charged and neutral particles for P by P annihilation. And it looks, and it's a small version of a high-energy physics particle detector. So it has had some microvertex tracking. It had some charged particle tracking. It had a 4-pi calorimeter out of cesium iodide crystals. And we did experiments with mainly stopped antiprotons, but as well to the maximum energy that Lear provided, which was something like square root of S 2.2. So, and then the results, and this picture I rather proudly show, because it was on the CERN annual report 1996. So this is the Dalitz plot that we did. Proton-antiproton goes to 3 pi 0, and it contains 700,000 events, so high statistics. And you see, everyone who knows Dalitz plot, that there's a lot of activity in there showing resonances. And the resonances that we discovered in there, which we were the first, is F0 1500. So it is a spin zero resonance, and you see here clearly a flat line. And since we have 3 identical pions in the final state, this resonance appears 3 times. You see it here, and you see it here. So this particle is very interesting because it's another spin zero, another scalar particle. So, but the determination of the contributing particles and their properties requires refined analysis methods, and clearly the interpretation of the states inside of the state's nature requires refined theory. So there one has to work together. Yes? Yeah, that is an interesting thing. There you find in all books about theory, I can give you references, you find a lot of discussion why there is at the 3 pi 0 Dalitz plot no intensity in the middle. In Muirhead, for example, you find discussions, but in modern books, it's disappeared. You know, in modern books, in Perkins, you don't even find a Dalitz plot anymore. Yes. And sometimes high-energy physicists, they ask me, what is a Dalitz plot? We have never heard about this. Yeah, they're starting to relearn it. But since it's not in the textbooks anymore, the students are not really aware of what it's useful for. Yeah? It's not black, but it's very depleted. There's not much happening in the resonance. Yeah.
can you see final state interactions?
You can see final state interactions, and they show up in the Dulles plot, but there one needs a theory to interpret it. Because, you know, we see that there is a change of intensity that we have to include. But this is a very good question, because often I get asked, especially by students, how do you analyze something like that? And I just want to show you an example how you do the analysis of something like that. So this is a different Dulles plot. So you take a Dulles plot and you have your data, and then you put in resonances that you in your model which you think are present. Your spin 0 resonances, spin 1, spin 2, and so on. And then you compare your modeled Dulles plot with the real data, and you sometimes find that the fit exceeds the data or the data exceeds the fit. So you have not a good description with your resonances that you put in. But then, and in this case, this was an exotic resonance that we found. I will not talk about it much further. But if we include this, then you see the differences between where the fit exceeds the data and the data exceeds the fit become simply only of statistical nature. And that means you have a good description and you know the contributing resonances that are present. So that is, there you need a model, and you might need final state interaction if somebody says that this is important for this. But you fit this with an isobar model? Yeah, we fit it with the isobar model because we don't really have another model. So isobar model means that the decay of particles goes through two particle decays. But because otherwise we don't have a better model. Yeah. 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 So, but what is important, and that is a lesson that we learned and that we will take into the future of PANDA, that actually statistics is really important. This is the same Dulles plot with another color coding, and this is a statistic of the 100 events. So it was bubble chamber statistics. So you see, it's no miracle if you have a statistics of a few hundred events that you don't see an F0 1500 here. You see some intensity, but you couldn't determine what it is. If you go to a statistics of 10 times more, yeah, still no F0 1500 visible. There's something in the middle. You would think that it's a blob, maybe a spin 2 resonance. If you go to 10,000 events, still the blob becomes more prominent, but you wouldn't bet on that there is a spin 0 resonance overlying here, that there are two resonances, and it really needs a statistic of 100,000 events to see that there's a line and a blob on top. So if you would like to do precision physics, you have to do a high statistics experiment. So the F0 1500 is a new resonance, a new scalar resonance that we discovered at Crystal Barrel. How about other gluon-rich environments? And this is a result from BES3. BES3 sees in the decay of eta-eta radiative J-psi decays, so of the J-psi into gamma eta-eta. You see the F0 1500 clearly, and you see something like the F0 1710. So it is confirmed by this. And nowadays, often I get asked, the F0 1500, but its existence is not really clear. That is not true. The F0 1500 has been studied in the meanwhile by many experiments. And if you look at many decay modes, and here you see it, this is an excerpt from the PDG. You see that it was studied precisely by many experiments. Some of the decay modes, and that becomes important for if you would like to interpret this particle, is or most of them were done by crystal barrel. And it's, of course, a huge advantage if you have one experiment that can study the decay of the particle in very different final states. So we have studied the pi0 eta eta Dales plot, where the F0 1500 shows up in the eta eta mode. We have studied the 3 pi0 I had already shown. We have studied an exotic channel pi0 k long, where we don't identify any of the kaons, and we see it. And then for the interpretation, it becomes very important that you study as well the A mesons, and you see here's a particle A01450 that we have studied. Now let's come to the interpretation. What is it? Well, the particles which are seen are the K0 star 1430 that has been known, and the A0 1450 I had shown you before. So that leaves in the meson, in the normal meson node, 2 open places here. These 2 open places could be filled by the resonances that we have found. And so the first resonance is the F0980, but you see already that the F0980 doesn't fit very well with the mass. It's much too low, and that is unusual for a meson node. So let's exclude it on the mass argument, and because there's another resonance which fits much better, this is F01370. And so there's one, then there's the F01710, and we found the F01500. So clearly, one particle is supernumerous. So it cannot be a normal scalar meson. But the question is now, which of these particles is a glue ball? Let's now turn to the meson production in 2 photon collisions. And as you remember, 2 photon collisions act as an anti-glue ball filter. And there are data from the Aleph collaboration, which did when lab was running, 2 photon physics. And they give an upper limit. Here you see where the F01500 would be, that they actually don't see anything, and they give an upper limit for the production of the F01500 in 2 photons and the subsequent decay into pi plus pi minus of 0.31 keV. So the F01500 does not seem to be produced in 2 photon collisions. When we started the glue ball business, glue ball investigating business, it was basically driven as well by the picture that a gluon, a high energetic gluon, doesn't care very much if it decays into an up and down quark anti-quark pair, or up anti-up, down anti-down, or strange anti-strange. So basically, one expected a kind of a flavor-blind decay. And a flavor-blind decay predicts that a glue ball should decay into pi pi, kk bar, eta eta, and eta eta prime with the ratios 3 to 4 to 1 and 0. So that was where we said, oh, that helps us to identify glue balls. We look if they do a flavor-blind decay. Well, the experimental observation of these 3 states is that the F01380 mainly decays into light quark states. So it seems to be an N and bar state. N stands for up or down quark. The F01500 decays much more into pions than kk bar. We see some decay into kk bar, but certainly not in this ratio here. And the F01710 has basically only be observed in its decay into kk bar. So what should we make out of that? And the Something which one has not taken into account, which nobody thought would, in the beginning that would be important, is the mixing of particles with the same quantum numbers. And those states, the F0, 1370, 1500, and 1710, they are relatively broad, and they're close together, so they overlap, and you find a mixing, and you can then do a mixing of a glue ball with a quark-anti-quark pair, and so on. And you can do some mixing schemes, some angles, as it is known for meson nonads. And this is something which I have taken from a lecture note from Claude Amsler. So the interpretation is that the F0 1370 is mainly a light quark state, that the F0 1500 is mainly has the most group component with an admixture of NN bar, and that the F0 1710 is a Strangionium member of the nonad. So this is a possible scenario that we have the A0 980, F0 980, the F0 1500, and the kappa 700 are 4 quark states. This is a modern interpretation. And these 4 quark states at longer distances show then up as KK bar molecules or pi molecules or pi k molecules. And so that those are the QQ bar members of the nonad, and the F0 1500 is the glue ball. I would like to point out something else to you. The F0 1710 is rather narrow, but that is not unusual for an SS bar state because it takes a longer time to decay. The F0 1500 is even more narrow, and this, in my eyes, is an indication that naturally a glue ball is not really very broad. So certainly it's very unusual for a light quark state, except the fact that it's heavily mixed, and mixing usually leads to a broadening of a state. There is a paper by Frank Close and Andrew Kirk, which compared the LHCb data from the B decays to this picture, and I just want to show you the last line here. In conclusion, the LHCb data appear to be consistent with the picture of scalar mesons below 1 GeV being tetraquark states, and those above 1 GeV being a canonical nonad mixed with a scalar glue ball. So this is what comes out of, if you compare modern data from LHCb and look at the lightest scalar nonad. So, and this clearly fits as well the lattice prediction, which said that the scalar glue ball should be around 1.6 GeV. So let's now come back to the predictions of the stringy hadron model. So how does the glue ball look in the stringy hadron model? So they make predictions on how glue balls behave on Regge trajectories, and we come back to that. And let me come. So, in the stringy hadron model, we said that the glue ball is a closed string rotating close to the wall. And how does a decay of a closed string look like? Well, a decay of a closed string could be that the string breaks in 2 points. You form a quark and an antiquark pair. You connect to one of the quark branes, and then you have a quark, then you have 2 meson states. And a split of such a decay of a meson where you have a quark and an anti-quark connected by a string would look in a similar way, that the string splits up and you produce a quark and an anti-quark pair. So this is a split of string with massive endpoints, except for a glue ball, you have to split the string at two ends. And so they make predictions on the decay width, and the decay width depends in this model on the length of the string. So how does it now come to the split of a string? Well, if we look at the decay of a meson, you have, for example, a heavy and a light quark meson. So you have a quark sitting on the heavy quark brane and one sitting on the light quark brane, and then the string fluctuates. And as soon as the string fluctuates and connects and reaches one of these branes, of these quark branes, then it can split. And so, for example, here you see how it was. If this fluctuation reached the light quark brane, then it splits into a quark-anti-quark pair, and you have two mesons. This would be the decay of a meson, or here it could even connect to a heavier quark brane, and then you have the decay into heavier mesons. So how does it look for a glue ball? Well, for a glue ball, you have the rotating string lying down here, and then you have the excitation of the string, and then it connects, for example, first to a light quark brane, but it has to have a second production of a quark-anti-quark pair. So it could be here, and then you have two mesons. So it could as well be the process that you first produce this, and then the string splits up, and you have two mesons that you need. So these mechanisms have been studied by existing data in the stringing hadron model, and they took existing data, for example, the decay of heavy quarkonia mesons, which is believed to be like J-psi decay or psi prime decay into gluons, and then they compared it with the predictions of their models. And so these are Zweig-suppressed channels, and so the Zweig-suppressed channels lead to a closed string which then falls down, so it should be closer to a glue ball, and that is what they studied. And so we have seen the B meson, and they come to results. So then, in their stringy hadron model, they need to have some tension of the string. It's not only the length of the string, which is associated with the energy, but as well the tension of the string. And the tension of the string, they get out of the mesons by saying that the tension is balanced by the relativistic centrifugal force. You remember it rotates in this in the cigar shape, and so this rotation produces some centrifugal force. So, and then once you have the tension, you apply it then as well to glue balls. So, and they take all existing data and to determine the properties, and then they fit the total decay width of hadron, including the Zweig-suppressed decays, which should then lead to a closed string, and they determine the branching ratios, and they're doing relatively well. Here you see the omega and the eta, and they do a fit of that, and compared with the experimental data, the red lines are their fits. And here is the rho and the pi. Only the So on wedge trajectories, only the pi is off, but I don't think that one does have to worry too much of the pi, because the pi is a special Goldstone boson, so it might be different. So here you see a fit to K star and K data, and here is the phi's, where there are two experimental phi's unknown. Okay, and then they do a fit of Glueballs, and the basic candidates of Glueballs are the flavorless hadrons, F0, the F0s, the 0++, and the F2s, the 2++. And they say what I presented, there are 9 F0 and 12 F2 candidates, and they put them into their theory, and they do a fit of Glueballs, and they claim, and this was a transparency which I had earlier, that the slope of the Glueball is different from the slope of a normal meson. So you see here, these are the normal mesons, the red and the blue, and these are the data, and this is the slope of a Glueball, and they argue that the slope of these particles help to distinguish a Glueball from a normal meson.
And what determines the slope is the tension?
Yes. And that picture actually fits that Glueballs are on wedge trajectories with lattice data. These are lattice data which predict that Glueballs, so there are several calculations on that, lie on wedge trajectories just like normal mesons. So, and then in the string hadron model, they did some fits. They assumed that the F0980 is a Glueball, the F01370, 1500, and 7010. And then they predicted their masses and their widths of the states. And they predicted the masses and the widths of the excited states, because they are on wedge trajectories. And you can get actually nice predictions, and I've taken out here the prediction that the F01500 is a ground state Glueball, and where you then have the other Glueballs. So here on this transparency, I just want to point out one thing. One of the main problems in identifying Glueball trajectories is simply the lack of experimental data, particularly in the mass region between 2.4 GeV and the CC bar threshold, where we found, where we expect the first excited states of the Glueballs to be found. And that is something that we have to tackle in future. And now let's look at the decay patterns of Glueballs. So we have to break the string. We have the rotating string here, and the rotating string does some fluctuations, and then if these fluctuations connect to a quark brane, then you form a quark anti-quark pair, and you have to do this twice. But clearly, what you see is in this model, then the width of the decay of a meson into two mesons depends on the length of the string and on the tension of the string. And for the width of the decay of a Glueball into two mesons, you get this formula here. And they get a hierarchy for the decay of Glueballs, of the Glueball into two light particles, to kk bar and to phi. And you have to remember that the branes sit at different energy level. So it's much easier for a vibrating string to reach the light quark brane than to reach the strange quark brane. And if you go to a kk bar, you have to produce one pair of strange quarks. And if you go to phi, you have to produce 4 strange quarks. So it's much less likely that, that you have a vibration of the string to reach twice the SS bar brane as the strange quark brane than to reach the light quark brane. And so their prediction is that the glue ball, the decay, for example, into omega-omega and K0, K0 and phi-phi would be 1 to 0.3 to 0.07. And
What is the value of the MQs that enter that? Are these constituent quark classes, 300 MeV, something like
yes, yes, yeah. And so this is actually a picture which fits the F0 1500 glue ball relatively well, because what we see is that the glue ball should decay mainly into NN bar with some SS bar component, and phi-phi we are clearly, it's not within the threshold. But if we compare it with the F0 1710, which some people favor as a glue ball, then it does not fit this picture because the strange quark brane is much too high in mass. So now let's look at the tensor particles, so the 2++ particles. And with the 2++ particles, there was a lot of excitement in the middle of 90s, even at the high energy physics conferences in Munich, for example. And because there were certain OZI violating particles discovered, these were the so-called Lindenbaum resonances in a pion-proton reaction going to phi-phi and something else. And these particles, they were called GT, GT prime, and GT double prime. So, and clearly one said, in view of the picture, that OZI violation processes should be gluon-rich, because a gluon couples flavor blind to the quarks. And so they were predicted to be glue balls, or very good glue ball candidates. And that led actually at Lear, the JetSet experiment, to study they could just reach the phi-phi threshold by going to the highest Lear energies. And they discovered that the proton-antiproton going to phi-phi cross-section rises sharply above the threshold. And so that was the main interpretation, but then it stopped Lear and one couldn't go any further. So just to tell you, these OZI violating processes we can continue at PANDA, so we can study phi-phi channels, but we can go even further, and we can study the production of a SS bar state and a CC bar state, like the phi j psi. And what I find interesting, if you're talking about dynamics, if you look at the D sub S bar and the D sub S states, you know, it's the same quark configuration in here. You have two strange quarks and two charm quarks, but arranged differently, and it would be, I think, very interesting just to compare how these processes proceed. But since we are talking about glue balls, let's come back to the 2++ glue balls, so the tensor glue balls. And here you see there are plenty of states which have been predicted with 2++ quantum numbers. Two states clearly stand out. This is the well-known F2 1270, and this is the F2 prime 15. This is the F2 1565, which one doesn't quite know. But you see, there are plenty of states here, and they are all overlapping. And I think that is the same picture that we get from Bess. The interpretation of these 2++ states above 2 in this mass region is a mess. And I think only precision data and good partial wave analysis can entangle this because even disentangle, yeah, you're right. Yep. Too late at night that I did the transparency. Yeah. Okay, so that is the situation with the tensor glue ball. And the last glue ball that one could tackle is the pseudoscalar glue ball, so the JPC 0 minus plus particles. And how is the situation there? Well, let's look at radiative J-psi decays. And in radiative J-psi decays, the best experiment in the channel J-psi goes to gamma 3 pi 0 has seen a clear evidence for the decay of the eta 1405. And if one looks now at gluonic suppressing two photon collisions, that was done by L3, then you see the F2 1285, but you see no eta 1440. So in the gluon-rich channel, we see a huge production of the eta 14040, and in the two photon, it's not produced, or it's produced below a certain upper limit. So what to make up? Because if we look at the predictions from lattice, and lattice predictions put the pseudoscalar glue ball close to the tensor, clearly at masses around above 2 GeV. And but with the eta 1405, it lies down here. Well, we might still but most of these actually lattice calculation were quenched lattice calculation. So that means they didn't take quark-antiquark pairs into account. But the mixing has to be taken into account. So you would like to have an unquenched calculation. And nowadays they produce, there are quite a number of groups which produce quenched, unquenched lattice calculations. And for most, so these are unquenched predictions, and for most channels, the unquenched corresponds to the quenched results. You see there are some mass differences, but not really that much, except there is a calculation of the pseudoscalar glue ball, and they are taken into account the eta prime mixing results from Chloe, and they found that you find in another paper is which cites this paper, one analysis of the decay properties of the 0 plus minus state suggested that large unquenching effects moved the quenched 0 minus plus glue ball from 2.6 to 1.4 GeV, close to experimental mass of the eta 1405. And so this is, nobody knows what's really going on with a pseudoscalar sector there, but clearly this fits a picture which we proposed in the year 2004, where we said that the glue ball, together with Antti Niemi and Ludwig Fadeev, the glue ball is a closed flux of color, and in order to prevent that it shrinks away, you have to introduce some twists or some knots which prevent the shrinking away. And but since a twist can be right-handed or left-handed, you would expect that the scalar glue ball and the pseudoscalar glue ball basically have the same mass, because the mass depends simply on the length of the closed string. And so this would fit our picture that the eta 1405 and the F0 1500 are the pseudoscalar and the scalar glue ball. And but nobody knows. So let me now turn to the last set of glue balls, other glue balls. And other glue balls, and this is just my personal view on a 1++ glue ball, and I think the X4140 is an excellent candidate for a 1++ glue ball. And because it decays into J-psi-phi, okay, that would be a flavor-blind decay. And it has been first seen by CDF, but it's seen as well by D0, and more recently by CMS and LHCb. LHCb, it's here at the beginning of the phase space. And what makes it as well interesting is that it's not seen by Bell in two-photon reactions. It's not produced in two-photon. They see nothing there. And with BESS, we try to look for it, but it's clearly too little statistics to tell if there is something, but it doesn't seem to be a huge peak. So that I find extremely interesting, that this particle appears in gluon-rich, like here we have proton, antiproton, or you have very high energetic proton collisions, and it's not produced in two photons, and it's extremely narrow. Look at it. Its width is 19 MeV. So that is rather particular. Okay, and now I come to the future. I hope that I convinced you that proton-antiproton collisions gluon-rich, and the advantage that we will have there concerning glue balls is that we can produce gluons of all kind of spins, no problem. Positive C parity, negative C parity, because you have multiple gluon states in between. And I think that is clearly a huge advantage that we have in future, so we can fill, hopefully, the Reggie trajectories, and we hopefully then can, just like as one understood atomic physics, by putting particles in Mendeleev's system, one could hope for understanding what the nature of glue balls is by studying plenty of glue balls and their properties. And so hadron physics, one should realize, is the only place on Earth where one can study non-abelian massless gauge boson interaction in a controlled manner. So two gluons or multiple gluons coming together. And why is this gauge boson interaction interesting? Well, you find it if you go to Feynman lectures on gravitation. You find speculation about graviton-graviton interaction. That is as well massless gauge boson interaction. I'm pretty sure that nobody will ever be able to measure graviton-graviton or study graviton-graviton interaction.
Never say never.
Well, yeah, but first the graviton has to do this discover. Okay, I say in my lifetime. And but here with glue balls, we might have a handle on understanding very fundamental things, and that's why I called glue balls fundamental. I hope you got my excitement. I called them exciting. But you saw as well that experimentally and from the theoretical interpretation, they are elusive. But that is what we are trying to change in future with the PANDA experiment. And with that, I would like to say muito obrigado, and thank you very much for listening.
Thank you, Ulrich, for this very exciting talk. Please, questions? Okay. To here, I don't know who was the first.
Up there.
You or him? You're not
up there he was first.
Okay, but maybe he saw. These people are very fast.
Just to ask, has anyone, the crucial thing, as you said, we live in a quantum world, so you cannot have, whether something is a glue ball or a state which has the same quantum numbers of a glue ball is not an observable. But on the there is mixing angles everywhere. But on the lattice, one can get away with doing a few more things. You can put in an extra term of the Lagrangian or something like that, a source term. Has anyone thought of a measurement which could be applied on the lattice, even like at a Gedanken experiment level, the lattice is strong enough, which tries to measure the mixing angle between a glue ball and an equivalent flavor configuration? Or even on the lattice, this is impossible?
Well, the problem is that the lattice, they cannot calculate so far decays. They don't make any decay predictions. And especially,
What you do in a lattice is you put operators on the lattice and then make measurements with these operators, right? And in the case of, let's say, a 0++ glue ball, you just put in all operators that have 0++ structure. And then what you can do once you identified your state, you can look what is the overlap of the states that you have with certain types of operators, right? Operators containing QQ states, operators containing non-QQ states. But this is all you can do. And this is not really determining a mixing angle or things like that. It's just, it gives you a vague idea of the weight between the different states, yes.
My question was about lattice. How lattice can help to identify the states with gluons. My question is, are the results, should you trust the results, or you still have to do some extrapolation for the physical limit, and the result could be very, very different?
Well, we would certainly appreciate, but I showed you the 1++ glue ball. There is no lattice calculation which predicts a 1++ glue ball. I asked Mike Pion, he doesn't know why there is no 1++ glue ball. He said, maybe we had problems, or we don't know, or we didn't have time. There is no prediction for the 1++ glue ball. And so, as well, I presented the different models. The different models, they come sometimes to the conclusion, the higher the mass of the glue ball is, the broader it might get. But I think I have an argument from experimental data which speaks against this. Because a 1-, glue ball is predicted by lattice between 3 and 4 GeV. This is exactly the region where we have the narrow charmonium 1-, states. If you have a broad glue ball there, it would overlap with those particles and they would not be narrow anymore. They would decay via the glue ball component. So in my view, what we see with the F01500 is extremely narrow. I think a natural glue ball might be even more narrow. And all this. So, but clearly, lattice calculations would help, definitely.
Just one more comment on your previous slide, where you said interaction between massless gluons, right? Massless gauge bosons. Of course, yes. Gluons are only massless in a non-interacting world, right? As soon as you switch on interaction, they become massive.
Yes.
So,
yeah, sure.
And we don't know whether gravitons have the same problems, right? So maybe the analogy between gluons and gravitons is not so close as one might think.
But since we don't know anything about graviton and we don't even understand the mass generation of the strong interaction, what this workshop is about here, I think that's, but it's a well-taken comment. We will learn about this. Yes.
More questions? George, you want?
Just as a sort of point, I think we've already seen graviton-graviton interactions because in neutron star systems, gravity is strongly nonlinear. That it's a classical graviton. It's exactly the same thing. When you quantize it, you have a graviton-graviton interaction. Yeah.
Okay.
It's h squared.
Okay. Some more questions? Yes.
I wanted to know, what is a pomeron?
A pomeron is a
Every time to be honest, nobody can explain.
To be honest, nobody knows it. It's a multi-gluon. It's a multi-gluon configuration. You might call it glue ball. It's a multi-gluon state. If it's formed a bound state or not, that I would not.
But it is colorless, right?
Yeah, it is colorless. Yeah.
More questions? Comments to Ulrich? Maybe I have a naive question that I think is very nice, your discussion.
Yeah.
You look that you think on constituent quarks. You mentioned something to Gaston. On the other side, when you talk about Glueballs, it looks that you're naively thinking about particles like constituent quarks. But the view you give with these brains and so on. So could you give some naive points on if there is a way nowadays, in view of the data, to have naive thoughts or to guide our intuition on these global states?
I think there is now more or less a common agreement that a glue ball is a multi-gluon configuration which has a particular form. You know, it runs on the lattice as a closed loop, in this string hadron model as a closed loop. So I think the picture that one had 20, 30 years ago, where one had a bag and then gluons in there, I think that is clearly too naive. So I think, closed flux of color, somehow that is a good picture that one could give too.
So partonic picture for Glueballs is off?
In my view, yes.
Yes, okay, I wanted to. Some more questions? So, okay.
But then in the string of pictures, what creates the mass of these glue balls?
What creates massive glue balls? The length of the string. That has the energy. The string has a certain tension.
Sure.
And so you have energy in that, and then the length of the string determines the masses of the glue balls.
No, this is very nice. I mean, I think people will continue to discuss during the coffee break. So let us thank Ulrich. So we are back at 11:30. Yes. Thank you.